Welcome to the Problems Channel Season 2, Episode 42, the episode which I titled How a Hoof Can Compute a Limit, because in this episode we will do precisely that. We will use a geometric object known as a hoof of Archimedes to evaluate a certain limit. But before we do that, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, it is a good idea for you to go to the homepage of this channel and in the channel's trailer section find the episode titled The Problems Channel How To. Watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2E42, we were asked to use specifically the divide and conquer problem solving approach in order to evaluate a limit that has the following structure. 1 over n raised to the third power, where n is a whole positive number such as 1, 2, 3, 4, 5, and so on. And that factor of 1 over n cubed is multiplied by a finite sum whose dummy summation variable k varies from 1 to the set number n, and the summand of this finite sum has the following structure. The dummy summation variable k is multiplied by the square root that is extracted from the following expression. N, the number n that figures in the upper boundary of this sum, squared minus k squared, where k again is the dummy summation variable. The condition or the predicate of this limit is shown over here. The set whole positive number n grows without bound, or n tends to positive infinity. If you have little or no problem solving experience, then it is likely that just about now you realize that this is some impossible abracadabra. If you have a little bit of a problem solving experience, then you probably realize that this limit is quite challenging, and it is. And if you have quite a bit of problem solving experience, then you realize that in order to evaluate that limit in an elegant or out of the box way, it is a good idea to use an auxiliary mathematical object or a helper mathematical object. And if you did not solve this problem correctly, completely, and on your own, here's a chance for you to do the right thing one more time. Practice mathematics correctly. Take this as a hint. In order to solve this problem, it is a good idea to introduce a helper geometric object in this case. Put this video on pause, walk away from the computer, think on your own at least for a while, and then come back and compare your ideas to ours. If you have a better idea, do not be shy. Please share your beautiful idea with our community in the comment section. But the intended, or at least my solution of this problem, is based on a helper geometric object known as the hoof of Archimedes, or sometimes referred to as the wedge of Archimedes. Before I show how the hoof of Archimedes is constructed, here is a short crash course on cylinders. For our purposes, all the cylinders out there can be sorted into two distinct piles. In other words, we can distinguish the cylinders that enclose a finite amount of volume and the cylinders that do not enclose the finite amount of volume. The cylinders that do not enclose a finite amount of volume come in two interesting flavors: parabolic and hyperbolic. In order to generate a parabolic cylinder, what we can do is, in plain English, take, for example, a parabola shown over here. This is a parabola, or a portion of a parabola. In theory, this curve runs into infinity on both sides, and then make many downward copies of that parabola and generate a sheet or a surface. In the old days, nowadays it's a manifold that looks as follows. And in order to generate a hyperbolic cylinder, we do the same thing, but instead of using a parabola as a generator of that surface, we use a hyperbola. Here on the left side, I try to show the hyperbolic cylinder, one part of whose surface we can see very well. The other one runs into us. Let's say it's foreshortened, but the idea is the same. The surface runs into infinity on both sides. We make many downward copies and thus generate a hyperbolic cylinder. For our purposes, we're not interested in these type of cylinders. In other words, parabolic and hyperbolic cylinders are off the table. Of interest to us are the cylinders that do enclose or trap a finite amount of volume, and these cylinders can also be sorted or separated into two distinct piles based on the type of a curve that forms its bottom and top, and based on the quality of the projection of the center of the top face of such a cylinder onto the bottom plane. That is, if the top and the bottom faces of a cylinder that encloses a finite volume is a circle, the same or two congruent circles, or a circle of one and the same radius are shown over here in red, then such a cylinder is called circular. And if the top and the bottom faces of such a cylinder are one and the same ellipse shown over here, then such a cylinder is called an elliptic cylinder. Separately, if the center over here, shown over here, recall that both a circle and a cylinder has a specific place called a center. Consequently, if the center of the top face of a cylinder orthogonally projects dead on to the center of the bottom face of that cylinder, then such a cylinder is called right. Otherwise, if the center of the top face of a cylinder does not project orthogonally onto the center of the bottom face, such a cylinder called oblique. In other words, in plain English, we can simply think about the oblique cylinders as follows. Take a right cylinder and we tilt its side surface one way or the other way. Here I showed one where we tilted the surface right a little bit, and then again. The fact that these two types of cylinders that enclose a finite amount of volume are independent means that a right cylinder can be circular and a right cylinder can be elliptic. When the right cylinder is circular, then the top and the bottom faces of such a cylinder are a circle of one and the same radius. And if the top and the bottom faces of a right cylinder is an ellipse with the same axis, the major and minor axis, the lengths of this axis are the same, then such a cylinder will be called right elliptic. Also, a cylinder very well may be oblique circular, or it can be oblique and elliptic. If an oblique cylinder is circular, that means again that the top and the bottom faces of such a cylinder is a circle of one and the same radius, but as I mentioned it before, the center of such a circle orthogonally projects not onto the center of the base face, which is a circle of the same radius. And again, an oblique cylinder can be elliptic all day long. That means that the surface of such an ellipse is slanted with respect to its base, but the top face and the bottom face of such a cylinder is what? Is an ellipse that has exactly the same major and minor axis. Now that we understand a little bit about cylinders, for our purposes in this problem, of interest to us will be a right circular cylinder. And we will use precisely a right circular cylinder in order to construct the hoof of Archimedes. If you have understood what we said about cylinders in the previous segment, then you should realize eventually that across all the types of cylinders that we have discussed so far, only one type of cylinders is the so-called solid of revolution, which means only one type of cylinders that we looked at so far can be generated by rotating a two-space shape about one of its elements. And what type of cylinders is that? Correct, this is a right circular cylinder that can be generated as follows. We know that the two-space shape, to which we refer as a rectangle, comes in two distinct flavors. A rectangle that is not a square and a rectangle that is a square. And these two shapes have very different, let me draw it over here, they have very different groups of rigid symmetries. A square has a group of symmetries that is isomorphic to the so-called dihedral group D4, and it has 8 elements in that group. That group is not commutative, but the group of rigid symmetries of a rectangle is isomorphic to the so-called Klein-4 group. That group has 4 elements. That group is commutative and designated usually with K4, for example. And the size of this group is 4. It has 4 elements. That group is commutative. So thanks to the theory of groups, we can say that a rectangle is twice as less symmetric as a square, and the square is twice as more symmetric as a rectangle that is not a square. Now we take at first a rectangle that is not a square, and we rotate it about one of its, let's say, longer sides. Let's say we rotate it about this side right here. This straight line that contains one of the longer sides of a rectangle becomes the axis of rotation and axis of symmetry of the resultant cylinder, and we rotate, let's say, in this direction. We rotate that rectangle by 2 over pi radians, and we generate the following right circular cylinder. The top will look of the cylinder will look that way, the bottom will look this way. This will be this side. This radius will be r over here, the same radius r over here. And if we make this rectangle, the generating rectangle, long enough, then we can say that, let's say, intuitively speaking, the resultant right circular cylinder will be taller than it is wider. If we take a rectangle that is not a square and flip it that way, we can rotate that rectangle about any one of its shorter sides, for example, this one right here. Then in this case, the straight line that contains that shorter side becomes, rotated this way, again by 2 pi radians, again becomes the axis of rotation and axis of symmetry of the resultant rectangle. Let's say it goes this way, so that the top face of this right circular cylinder will be this guy, the bottom face will be this guy. This is a cylinder which is more wider than it is taller, and with the square it doesn't really matter. We can rotate that square about any one of its sides this way by 2 pi radians, so we get a cylinder that looks as follows. This cylinder will be evidently twice as wide as it is tall, and in the near future we will solve an interesting physics problem in which we will answer the following question: which shape, a cylinder, a right circular cylinder just like it, or a comparably sized cube, is easier or more difficult to tip over or flip over on its side? Now that we understand how a right circular cylinder can be generated, again, I recommend that you guys play around and try to draw the cylinders in all sorts of positions to develop a better feel for this mathematical object. But right now we'll jump to the construction of a hoof of Archimedes, and that construction looks as follows. We begin with a right circular cylinder. Let's say we begin with this guy, runs this way, this side runs this way. This will be the circular base. This is the center of the base face or the bottom face. This will be, let's say, the center of the top face. It doesn't matter, but the characteristic feature of the hoof of Archimedes is the following. We cut this right circular cylinder with a plane that passes precisely through one of the diameters of, let's say, the base face or circular base face of this right circular cylinder. Let's say we cut it this way, and this is the result of the intersection of the cutting plane of this right circular cylinder, and this plane runs this way from northwest to southeast, let's say. When such a cutting plane intersects the outer curving surface of a cylinder, then such an intersection will generate a quadratic curve that we all know and love. It's called an ellipse, and technically this will be an elliptic arc or an arc of an ellipse. And this arc will run which way? It will run this way. Let's say it will run this way up to here, and then it will close in on this guy over here, and voila, we have generated a hoof of Archimedes. This plane over here has the shape of a portion of an ellipse. This part right here is curved, and the bottom of the hoof, so to speak, is what? Is precisely a semicircle of radius r. In other words, this distance and this distance, this is r, this is r. We'll look in detail at all this material in the next segment. But whenever we begin working with a new geometric object, it doesn't have to be a solid or a surface. It can be any geometric object in general. We should try to develop a deeper, better, or more intimate relationship with it. In this case, one way to do so is to try to draw this new to us shape in all sorts of positions and orientations, ideally from your mind, from your imagination. If you cannot draw this new solid from your imagination, then it is fine. Use any one of software packages available to you. But here we will do this cutting one more time together. Let's say we cut our right circular cylinder again with the plane, but this time we chop off the upper right portion of the plane. Remember that for a hoof of Archimedes to be the hoof of Archimedes, this plane has to cut the face, the corresponding face of the right circular cylinder or of a generating cylinder along one of its diameters. You cannot cut it here or here. It has to pass, the plane has to pass through the center of one of the faces. And then we chop off the cylinder this way, so the elliptic arc will run which way? It will run this way, it will curve, and then close in to over here, and voila. Look at this. This will be the semicircular top of our hoof. This will be the curving part, and this will be the plane that is delineated by an ellipse. Okay, so we understand more or less how these things work with the vertically oriented right circular cylinder. Let's flip our cylinder to the side. Let's say we'll put our cylinder this way, we'll put it this way, and it will run this way. So let's cut a few hoofs of Archimedes from this cylinder. This is the center of one of its faces. This is the center of another of its faces. So which way would you like to cut this specific hoof of Archimedes? Let's say we cut it this way with the plane that runs from northeast to southwest. So this plane, remember, has to cut the corresponding face along one of its diameters, so it has to pass through the center. And then because we cut this cylinder, right circular cylinder with the plane that way, which way the elliptic arc will run? Correct, this elliptic arc will run this way. It will go this way, curve, and then come back on the other side of the cylinder this way. So this again will be our semicircular base of the hoof. This will be the curving surface. This one curves. And the elliptic shape that delineates the plane that forms the other side of the hoof. Okay, let's cut a little bit maybe from here, from the bottom right. Let's do another one. We first want to position this volume in our mind's eye, and then what do? We cut it, for example, this way. This is how the plane will intersect from this point to this point. And because we cut this cylinder also with the same plane, then the elliptic arc will run which way? It will run this way right here, this way, and then it will curve and come back. And where is the hoof? The hoof is what, right here on the bottom. So this surface curves. Behind we cannot see is what? Is the semicircular base of the hoof, and this plane right here is delineated by an arc of the corresponding ellipse. Play some more. Let's throw this cylinder into awkward position, into awkward angle. I have some room over here, so let's do it this way. Let's flip this guy in this direction, this way, and then we'll launch him here, and then this way. You see, this is our cylinder. This is the center of one face. This is the center of the other face. So what do? Let's cut it along the top face like this. And then we chop off this part over here. So that means that the elliptic arc will run this way and terminate over here. You see, this is the hoof of Archimedes. Again, this top over here, this top is what? Is a half circle or semicircle. This part over here curves in a cylindrical curvature way, like this. And this is our plane that is delineated by an arc of an ellipse. Again, we can vary this plane in different ways as long as we have an interesting non-trivial volume. Okay, let's do one more. Maybe let's cut something from this side. Let's cut it this way, for example. The plane will run through the center of this face from here to here. So far, so good. And we chop off our right circular plane this way. Which way the elliptic arc will run over here? Well, in your mind's eye, you see that it runs this way. It goes up to here, and then it curves and comes back through the other surface of the cylinder that we cannot see. Again, this is the plane. It is delineated by an arc of an ellipse. This part over here curves. This is the curving part. See? And this is our hoof, which is a solid that is trapped. How? It's trapped inside a right circular cylinder. In this case, for example, to the left of the plane, under the plane, above this face over here, about the left face, and inside to the right of the curving surface. This is our hoof of Archimedes. This is the solid that unlocks an elegant solution of the mathematical problem S2E42. And before we jump into the underlying computations, I would like to remark one more time that mathematics is an art. Mathematics is an art of telling a story. Mathematics is an art of telling a story of how and why, and in order to come up with that story, we need to exhibit a certain amount of technical ingenuity and creativity, and the process of exhibiting ingenuity and creativity is precisely the process of doing mathematics. In this case, what is mathematics and what is not mathematics in our problem? In my humble, not professional opinion, the mathematics in this case is the process of generating and regenerating, combining and recombining ideas, because an idea is a first-class citizen in mathematics, and it was the process of generating this idea of fishing out from your web of mathematical knowledge this specific solid, and then asking the question, what will happen if? And now that we understand how the hoof of Archimedes is constructed, we will engage in a small amount of symbolic shuffling. But again, I want to make sure that everyone in the audience understands that the symbolic shuffling that we're about to engage into is, in some sense, not mathematics. And if you guys think that I'm too harsh, then okay, fine, lesser mathematics. And this symbolic shuffling is always a means to an end. This is not the mathematics. The mathematics here is the process of generating and regenerating, combining and recombining, the idea of searching for a right auxiliary object that unlocks an elegant solution of the problem. Whatever follows this idea is symbolic shuffling, and we can say that symbolic shuffling follows an idea. Now that we understand how a hoof of Archimedes can be constructed, we can develop a battle plan for solving the mathematical problem S2E42, which is: recall that if we want to apply the divide and conquer problem solving approach to the process of generating a solution of this or that technical problem, we should try to carry out the following 3 steps. First, we should try to identify a whole, and then we should try to divide that whole into a number of smaller and simpler primitive parts. In the step number 2, we should try to generate or find all the solutions of all the primitive parts. And in the third and the final step of the divide and conquer problem solving approach, we should try to find a way to combine all the solutions of all the smaller and simpler primitive parts into a solution of the whole. My idea for applying the divide and conquer problem solving approach to the process of generating a solution for the problem S2M44 is precisely that. For a whole, or for the divide and conquer whole, I suggest that we use precisely a hoof of Archimedes, which I already explained what it is and how to construct it. That takes care of the first part of the first step. Now, for the second part of the first step, when we're asked to divide our whole into a number of smaller and simpler primitive parts, again, my idea is to do it in 2 different ways. In other words, for the first divide and conquer step, we will partition or tile our whole, a hoof of Archimedes, with smaller and simpler primitive parts, each of which looks like a triangular prism shown over here in the red on the right hand side of your screen over here. And do not worry, I'll explain in all the details how this triangular prism comes into life, what does it mean, and all the details we'll discuss in the next segment. And we will use this specific smaller and simpler primitive parts, triangular prisms, in order to carry out the second step of the divide and conquer problem solving approach, where in this case it will mean to express the volume of one smaller and simpler primitive part, a triangular prism, in terms of the locally available material. And that is exactly what it means to say that solve each and every smaller and simpler primitive part. In this case, a solution of a smaller and simpler primitive parts means expressing its volume in terms of the locally available material. We'll dive into details. And still, as the second part of the first step of the divide and conquer problem solving approach, we were asked to divide our whole into a number of smaller and simpler primitive parts, I suggest that this time we tile or we assemble our whole not with triangular prisms as shown in red on the right hand side of your screen, but with rectangular prisms. These rectangular prisms are shown in red on the left hand side of your screen. This is the part. Also, do not worry, I'll explain in details how this rectangular prisms come into be, and this will carry us into the second step of the divide and conquer problem solving approach, in which case to solve each and every rectangular prism simply means to express the volume of that smaller and simpler primitive part, or the volume of this rectangular prism, in terms of locally available material, which is the same as the material that we will use in the first case. Then we will compute the volume of the whole one way and the other way. And because we're computing the volume of one and the same whole, we will claim that these two expressions that we will obtain as a result of this executing this idea must be equal one another, precisely because this will be the volume of one and the same solid. And the third and the final step of divide and conquer problem solving approach, find a way to combine the solutions of all the smaller and simpler primitive parts into a solution of the whole, will amount to the following observation. Our smaller and simpler primitive parts do not really match exactly the given whole. They only match it approximately. And in order to be able to remove this approximation sign in the volume of the hoof, which is expressed as a sum of volumes of the primitive parts in both cases via triangular prisms or via rectangular prisms, we'll have to pass to the limit where n is our favorite usual suspect, will precisely grow without bound, or n will tend to positive infinity. Now that we understand what the battle plan is, let us deep dive into the case when we partition the whole, a hoof of Archimedes, with smaller and simpler primitive parts, which look like precisely triangular prisms. Also, one more time before we deep dive into the underlying computations, when we represent the volume of one and the same or fixed, in some sense, hoof of Archimedes with triangular prisms shown on the right hand side of your screen in red, then we will obtain a limit that is baby simple, and we will all know how to compute it. And even if you do not know what the mathematical limit is, do not worry, you will still get the hang of it. That computation will be straightforward. If, on the other hand, we take one and the same fixed hoof of Archimedes and represent its volume as a collection of rectangular prisms, then we will get the scary looking limit that was given in the problem S2E42, and by equating the two expressions that we will obtain as a result of these computations, we will reveal precisely the answer, we'll find the answer, and we will know what the value of that limit is. So here, when we represent the volume of one and the same fixed hoof of Archimedes with triangular prisms, A, B, C, shown on the right-hand side of your screen in red, then we have the following setup. The point G over here and the point F shown over here, the point G, the point F, they represent a line segment or a diameter of the circular base of the generating right circular cylinder, and we all by now know and understand what it means, because a hoof of Archimedes is generated precisely by a right circular cylinder. In other words, GF is a diameter of a circular base of the generating right circular cylinder. The point O is the center of that circular base, and that means that the distance from the point G to the point F, shown over here, is precisely 2r, and the length of the radius of the circular base of the right circular cylinder from which this hoof is generated is precisely the locally available material. In terms of r, we will work from now on, and we will express the volume of a hoof of Archimedes precisely as a function of r and the function of h, which is in plain English the height of the hoof of Archimedes, and we will get to it in a moment. Now recall that when we cut the generating right circular cylinder with a plane, as we did many times in the previous segment, then the cutting plane will have one point in common over here with the curving side surface of the cylinder. We will name that point E, and precisely because the structure of this geometric object, to which we refer as a right circular cylinder, is what it is, the orthogonal projection of the point E onto the base plane of that cylinder will fall precisely on the point D, and that point will sit somewhere on the semicircle, which is the base of this hoof. Now, it so happens that if we connect the point D with the point E, so I showed it over here, the distance between the points D and E is h, designated with the lowercase h. I will refer to it as the height of a hoof, of this hoof of Archimedes, dE right here. And precisely because of the way this, again, geometric object known as a right circular cylinder works, if we connect the point O with the point D, shown in red over here with a dashed line, because in theory, if a line is dashed, technically we do not really see it. We kind of use special mathematical goggles to see through or peer through the solid. So that line will be orthogonal to the diameter GF, but the distances from the point O to all these points, to the point G, to the point F, and to the point D will be one and the same, and that distance will be what? The distance will be precisely the length of the radius. So the distance from the point O to the point G, from O to G, from the point O to the point F, from the point O to the point F, and from the point O to the point D, from the point F to the, from the point O to the point D. Let's say O D is still R. Is still R. Let me put it like this. And as I said, due to the fact that, again, remember, the cylinders that enclose a finite amount of volume come into fundamental types, right or oblique. Because we are using the right circular cylinder, the angle at D, the interior angle at D over here, is precisely right. In other words, the angle ODE is right. That means that if we connect the point O with the point E, this will be a straight line that is basically in this case, by the looks of it, it's the major semi-axis of the elliptical curve, or of the ellipse. Which one? F, E, C, G, of this elliptic curve. This is straight line. It's 1/2 of its major axis. Then the triangle ODE will be right. The triangle ODE will be right, with the magnitude of the interior angle at D which is precisely right, or pi over 2 radians, or 90 degrees. And again, due to the symmetry of the arrangement, the plane ODE will be the plane of symmetry of the hoof of Archimedes, thus constructed. And what does that mean to us tactically? Tactically, that means to us that we just have to fight the fight with 1/2 of this hoof that's located to the left or to the right of the plane of symmetry ODE. I will use the left half. You guys can use the right half. It doesn't really matter. But it is important to understand that once we carry out this second step and find the volume of the triangular prism ABC, which I'm about to discuss in the next segment, then we will put all these smaller and simpler primitive parts, all these thin triangular prisms together. Then for the volume of the whole, we'll have to multiply that summed volume by 2. Now that we understand the basic setup of what do these points mean with our hoof of Archimedes, again, one more time, I want to make sure that you guys understand R, the length of the radius of the base face of the generating right circular cylinder, and the height, H, is the locally available material. We'll work in terms of R and H at all times, and we will express, in this case, the volume of this hoof. It will be a function of R and H. And now that we understand that material, let us wrap our brain around where and how does the triangular prism ABC, shown on the right hand side of your screen, comes to life. At first blush, or on the first reading, the divide and conquer problem solving approach may come across as big, scary, and mysterious. And do not worry, this is the case with all technical information everywhere: mathematics, theoretical physics, computer science. This is the case. But once you step up close and get to know that problem solving approach, you will realize that it is just as beautiful as it is powerful, and yes, it has a number of moving parts that must be put together just precisely so. No extra part can be added, no existing part can be removed. But once you play with this approach long enough, you will understand that here and now the divide and conquer problem solving approach earns its stripes or earns its paycheck, so to speak. If you want to use the red color again, let's take our semicircular base of our hoof, turn it around and flip it on the plane and look at it this way. So this will be the point where this will be the point G. This will be the point G. This will be the point F. So far so good. Point F. Somewhere in the middle, somewhere here in the middle, the monkey in the middle, will be the point O. So our favorite diameter will be this line segment. Then on top of this diameter, we build a semicircle. See, like this. Let's pretend this is a semicircle where the point D will be. The point D will be right here. The point D will be right here. This is the point D. Let's designate it with D. This is the point D. This angle is right. This is radius R. This is radius R. Here runs the generating side of the cylinder. Point E is hanging somewhere, and the hoof goes somewhere this way. So what do we do now? Well, we put the divide and conquer problem solving approach to work carefully. We can work again due to the symmetry. Remember, we just have to fight the fight with one half of the hoof, and the other one we don't have to worry about. So which half you pick doesn't really matter. You can work with the left part, you can work with the right one. Try just to make sure that you guys understand what's going on. Work with the other part compared to with the one that I picked. I picked the left one. So now we take our radius R. This is the guy, radius R, right? This is our radius. And we unleash the mighty power of the divide and conquer problem solving approach on that poor little radius. We divide that radius in n line segments of equal length, and then we, let's say, count these smaller line segments with the points here, 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 and here, this way. So this will be the point number 1, this will be the point number 2, this will be the point number 3, and so on. Let's say this one will be the point number K. Now, through all these points, we construct straight lines perpendicular to that radius, like so. Construct straight lines. They will intersect our hoof, or the base of our hoof, at certain points. See, at this point, this point, this point, this point, all these points will run on the periphery of the semicircle. These are the points, like we go here, here, here. I do not want to convolute this drawing more than I have to, but you understand we cut this line segment right here into many line segments of equal length. What is the length of each line segment? Well, if we divide the distance R into n equal parts, the length of each line segment will be R over n, where n is an arbitrary whole positive number, 1, 2, 3, 4, 5, and so on. This is precisely where our points A and B come in. You see points A and B come in. Let's say this will be our point A. Which one did I designate with K? This one, okay. Let's say this is the point A. This is the point A. And this is the point B. See this guy right here. So now we pull the maneuver that you will learn about in college many times over. We construct another set of straight lines that are perpendicular to these straight lines until they intersect the immediate neighbor to its right. Let's say this one, then this one, then this one, then this one, and this one, and this one, and this one. You see, and then the resultant rectangle over here, this is the guy, see, will be precisely one side of it will be this side of the triangular prism, this guy. This is the band, this is the narrow strip. That is the length. Let's say we can throw some numbers. Let's say we name this point K, or let's name it Q. Let's name this point R. You see, like this. So then R over N will be, let's write it down over here, the distance from the point A to the point R, the distance from the point A to the point R will be precisely R over N. This distance is R over N, this distance is R, and so on. So we get these vertical strips, this one, this one, this one, and this one, and we stretch it out into a triangular prism this time. So this prism right here, A, B, and C. Now, this triangular prism, you can do, we discussed this mechanism called a net of a solid. This time it's not a net. I just made take two helpful pieces of paper, cut to size. They're pretty much identical size. And then you glue it together into a smaller and simpler primitive part that is a triangular prism. It looks this way on one side. It has this thickness on the other side. It has the same thickness all over. It is the same shape all over, just to make sure that you guys understand. You can see it better. No mystery over here. So with this smaller and simpler primitive parts, you see we tile, bam, bam, bam. That's how we tile up the left side, the left half of this hoof of Archimedes. You guys understand it. So here, the way these triangular prisms are positioned is precisely this way. You see, this is how these guys are positioned. So this is the angle right here of our plane. It goes like this, and that is our smaller and simpler primitive part. What is the whole? The whole is this particular fixed hoof of Archimedes. What is the smaller and simpler primitive part? A triangular prism positioned that way. And what is this thickness over here? This way, and actually this way. So in other words, this thickness, and this thickness. What is it? Well, we know what it is. It is this suspect right here. It's R over N, because we partition that line segment into N smaller line segments of the same length, R over N. And now that we understand where the point A, the point B, and the point C, it sits somewhere over here on the outer surface of our hoof right here. That's how it comes to be. Now we understand what it is, and we are done. In this case, we're done with the first stage of the divide and conquer problem solving approach. We identified the whole. The whole is this fixed hoof of Archimedes. We identified the smaller and simpler primitive part, the triangular prisms. We tile our volume with the smaller and simpler primitive parts. And now we want to move on to the second step of the divide and conquer problem solving approach, where we want to express the volume of each and every triangular prism in terms of locally available material. What is the locally available material? The locally available material will be R, it will be H, and it will be apparently N, and some number of line segments. If, let's say, we count our direction from the point O, we take this to be our proverbial origin, and we count the numbers this way, as I showed over here. So this will be the kth, primitive part, and in the next segment we will compute the volume of the kth part in terms of the locally available material. Now, on this channel, you will see it many times over, and if you practice mathematics correctly, as we suggested in Season 1, Episode 2, you will experience it for yourself firsthand, that a successful mathematical idea leads to computations that are mild, that are pleasant to carry out, and that are less error-prone, and conversely, a not successful mathematical idea leads to computations that are just grisly, boring, and error-prone. And again, once you watch this episode 2 or 3 times, several times, and you realize that it's not that difficult in reality as it sounds on the first hearing, you will see that these computations are actually quite straightforward and quite pleasant. And let us do it. The volume of the volume of the kth primitive part will be what? It may be helpful for you guys to see, to work or think about our smaller and simpler primitive part, which is a triangular prism, as follows. Instead of looking at it this way, we will temporarily flip it this way. And once you look at it this way, it is basically what? Well, it is one half of a brick, or one half is a book, where a book is a good model of a rectangular prism. And we all know that the solution of this primitive part is already known to us, or does not require an introduction of new ideas. If here, right now, in some sense, we are inventing the integral calculus and all the beautiful machinery that comes with it, here the process of computing or expressing the volume of a smaller and simpler primitive part does not require an introduction of new ideas, because the shape over here in some sense is rectangular. There are no curves, no complications. We know the volume of such a solid is what? The area of the base. In this case, we will take the triangle ABC, that side over here, we will take it as a base, times what? Times the height. And everything is uniform, rectangular, beautiful, and straightforward. No introduction of new ideas is needed. As such, the volume of the kth primitive part, or of the triangular prism, is what? The area of the triangle ABC times its height this time. And what is the height? Well, you go back to your record just a few seconds ago, you saw my drawing over here. That's the place where the divide and conquer problem solving approach left all the way to the bank. And that height in this case is basically the width of our prism, and that width is uniform. We agree that this is R divided by N. Now, what is the area of the triangle ABC? This triangle, by the way, is right, again, by construction, by the way the hoof works, and by the way the geometry of a right circular cylinder works out. So the triangle ABC is right. And what is the area of that triangle expressed in terms of the locally available material? Let's write it down over here. It will be 1/2 of the length of the side AB, this side, times it's the length of the side BC, times the width of our uniform line segments into which we cut the radius OG over here, R over N. Now, what can we say about the length of the side BC? Think about it on your own. Again, do not try your best not to listen to my solution as it unfolds non-stop. Apply your effort. Over here, I'm giving you such a time point. Put this video on pause, walk away from the computer, think on your own. How would you recover the length of the side BC in terms of the locally available material? Then come back, compare your idea to mine. The way I would do it is as follows. The triangle ABC and the triangle ODE are both what? They are both right. They have precisely the same angles. This angle is the same. This angle over here is the same. Consequently, which one here? This angle and these angles are the same. So by AAA, by angle, these triangles are what? These triangles are similar. And what does this tell us? Well, it tells us that we can go back to Euclid's Elements, Book 6, Proposition 4, which says what? The lengths of the sides about equal angles are in the same proportion where the corresponding sides lie opposite the equal angles. What does it mean? Well, let's construct the ratio. Write it down. I will not write it down over here on the desk to save space, but in your paperwork you guys do. We report the right triangle ABC by AAA is similar to the right triangle ODE. This can be proven. This is how the geometry of the right circular cylinder works. Wonderful. And from that observation, we have what? The length of the side AB. We're trying to find BC. Okay, let's write down BC first. So the length BC is in the same ratio to the length AB. Let's see. The length BC is in the same ratio to the side BA as what? As the height of our hoof. So that will be the line segment what? DE to the line segment OD. But we already know what that is. DE is the height, H. And what is OD? OD is the radius, of the circular base of the generating cylinder. And what does it mean? Well, we express BC from this equation over here. And what does that mean? Let's write it over here. The length BC is equal to what? AB times H over R. H over R. We will understand where this came from. Right triangles, similar triangles, Euclid's book 6 proposition 4, sides about the same, equal angles are in the same ratio. So now we take the expression for BC, this portion over here, and we slug it into this formula over here. What do we have? Here we'll continue, let's say on this side. What will we have? Well, we will have AB times AB. This will be AB squared over 2 times H over R times H over R times R over N times R over N. What do we see? We see another miracle. R and R. R in the numerator, R in the denominator cancel out. And what do we have in the end? In the end, we have the following expression. The distance between the points AB squared divided by 2n multiplied by h. And now the question is, what will we do with the square of the distance AB? Well, again, this is where the success of a good mathematical idea comes from. Look at this. AB, remember how we constructed the line segment AB. It is perpendicular to the diameter GF. And what does it mean? It means that if we connect the point O with the point B, like so, what will we have? We'll have, write it down, the triangle OAB is right with the magnitude of the interior angle at A being pi over 2 radians or 90 degrees. And what is the distance OB? Precisely, this distance is R, is the same guy, the same R. The distance from O to B is the same as the distance from O to D, from O to F, and then O to G. This, in the base of the hoof, we have a wonderful circle. And from the Pythagorean theorem, for the square of the distance AB, what do we have? Let's keep writing it over here. So we have H over 2n. H over 2n, just to make sure that you guys understand my scribbles, H over 2n times the square of AB, which is by Pythagorean theorem, is what? R square minus what? Minus OA squared. So far so good. This distance right here. This guy. OA squared. And what is OA squared? Well, remember, you guys keep track of this. I will erase this material. You keep it in your records. Remember how we obtained our triangle with prisms. We cut the radius OG into n smaller line segments of uniform length, R over n. And then what did we say? We said that we'll take the point O as our origin, and we will count the numbers right to left this way or this way. So what is the distance OA? OA. Well, OA, let's say OA is what? It's K, because this is the kth volume counted from O towards G, the kth volume. So K, because the distances are uniform, distances which ones? R over N, exactly, R over N. So this is the locally available material. Put this guy over here. What do we have for the volume? Let's put it this way. What do we have for the volume of the kth primitive part? We have H over 2n, H over S2n times r squared minus k squared times r squared over n squared. So far so good. This maneuver should cause no problems. This is all straightforward, in some sense middle school arithmetic. We're not going beyond right Euclidean triangles. How difficult is that? The volume of the primitive part is the area of the base times the height. The height is r over n. The height is this thickness. The area of the triangle ABC is half product of the length of its two sides. One side is recovered from book 6 proposition 4, similar triangles, and the other half is recovered by the other side. The length of the other side is recovered from what? From the Pythagorean theorem, exactly. So here's what we have for our expression, and now it gets a little bit messy. I will take a few seconds to erase the board, but now we will massage this expression just slightly so that we prepare it for the final step when we sum all these volumes together. But you guys can carry on and proceed on in your paperwork without waiting for me. Awesome, I took the formula for the volume of the kth primitive part, a triangular prism shown over here, and from the bottom of the board I moved it to the top. I factored out r squared. Remember, we had r squared minus k squared times r squared over n squared. Put everything in the parentheses under one and the same denominator, which is n squared. Move it out. N squared collides with n cubed. So in a way, you can already see something similar, something familiar with the limit that we were given in the problem statement here, but it's not the same. It's actually much more pleasant. And now we are taking on the third and the final step of the divide and conquer problem solving approach, where we find the way to combine the solutions, or all the solutions of all the smaller and simpler primitive parts, into a solution of a whole. What does it mean, combine the solutions of the parts into a solution of the whole? Well, in this case, if we simply take, let's say we take for v prime, we will designate what? I'll write it down, I'll write down the sum, and then you guys will understand what is going on. If we sum all the primitive volumes vk, where k runs the dummy summation variable, k runs from 1 to n, n is a arbitrary whole positive number, 1 to 3, and so on, what will we have? Well, we will have a certain volume. This will model the volume of the half, in this case the left half of the hoof of Archimedes. But what relation will be between this exact sum and exact number with reference to the volume of the hoof? What is going on here? Those in the audience who said the approximate sign belongs over here are correct. This is precisely the idea. The sum total of the primitive parts is not an exact match for the volume of this complicated whole. That is why we, in a sense, applying this divide and conquer problem solving approach to a difficult problem. An approximate sign reflects the fact that, remember, in our circular arcs we had this pesky little triangles. This is the, in some sense, the error, or the delta, if you will, the delta between the sum total of all the volumes of the primitive parts and the exact volume of the hoof. But the idea here is the following. If we make the number of such parts larger and larger, then the width of each, remember the function that reflects the width of each part, r over n. So when n grows very, very large, the width of each triangular prism gets smaller and smaller and smaller, and that happens what? Overlooking a large amount of gory details. It means that this part becomes narrower and narrower, and it models or approximates the whole better and better. And if we want to remove the approximation sign, what will we have to say? Well, we will have to say, let me erase this too, like this. So we will have to say that the equal sign will be in which case? When we apply the mathematical limit to this sum, when n tends to positive infinity. And what does that mean? Well, we grab this expression and we simply crawl it through our limit. So we'll have the limit when n tends to positive infinity of what? Let's say h, r squared, and 2 are constant. They can be carried out through the summation sign because they do not depend on the dummy summation variable, and they can be carried through the limit. So in this case, I will write it down just so we wrap our brains around it. hr squared over 2 n cubed. And what do we have here? Here we have the following sum. K runs from 1 to n. And what is this sum? N squared minus k squared. Now, these finite sums, these finite sums usually come out in reality once we step away from this carefully orchestrated situation, become quite horrible, and I'm not even sure if there is a machinery to always compute them in an algorithmic way, but here the sum comes out quite pleasant. So let us carry out this computation together. So for this limit, we have again h r squared 2 we can carve this out and carry out from under the limit, because again, this is a constant, does not depend on the dummy summation variable, does not depend on n, so we write it here, h r squared over 2, and obviously I forgot the multiply this guy by 2, because remember we have these 2 halves, so 2 times here, 2 times, and 2 times, we'll cancel these guys out, times the limit when n tends to positive infinity of what? Let us do this together. The first sum is triviality itself. N squared does not depend on the dummy summation variable. We'll factor it out, take it out from under the sum sign. We have the sum of n ones. N times n squared becomes what? N cubed. Correct. And here I forgot apparently 1 over n cubed times. And what is the sum of the first n consecutive squares of first n consecutive whole numbers, positive numbers? Well, we did it in our previous segments. We remember this formula. This is 1/6 times n plus 1 times 2n plus 1. This is our limit. One more time. The volume of the whole, this is our third step, is the limit of the sum of the volumes of all the primitive parts multiplied by 2. Here I apologize, I forgot 2 on the first go. That limit of the sum becomes twice the limit of this expression over here. Again, 2 times hr squared over 2. These two guys will cancel out in a few seconds. And here we have the limit of what? 1 over n cubed, 1 over n cubed times n cubed minus this seemingly horrible expression. But again, it turns out that this is actually a baby limit, and we will compute it together in the next segment. Very good. Now we take the formula for the exact volume of our hoof of Archimedes, V. Remember, we cancel the 2's out. What will we have left? H times r squared. H is the height of our hoof of Archimedes. R is the length of the radius of its semicircular base, times the following limit when n tends to positive infinity of 1 over n cubed, and in parentheses we have n cubed minus 1/6 times n plus 1 times 2n plus 1. Again, early on, your first semester, first year in college, or if you're brave enough, you can learn all these things in high school. These things are not that complicated. We carry out this limit as follows. We compute it as follows. Again, hr, survive this transition without a change, limit n tends to positive infinity. Let's do this together. N cubed, n cubed. Factor the n cubed out from these parentheses. And what do we have over here? Exactly. Over here in this sum and over here, there's lurking another n cubed. So when we factor out n cubed and n cubed cancel each other out. And what do we have in the end? In the end, we have 1 minus 1, 6. Okay, one copy of n is gone, another copy goes over here, another copy goes over here. N cubed, everything is good. So we have 1 plus 1 over n times 2 plus 1 over n. It's that straightforward, no complications. Divide both sides, both summands here by n, divide both summands over here by n, and this is what we have. Now let's keep moving on. H times r squared times the limit of n tending to positive infinity of what? 1 minus 1, 6. Let's do this together. 1 over 2 is 2 plus, what is it? 1 over n. 1 over n plus 2 over n plus 1 over n squared. Agreed? 1 times 2 is 2. 1 times over n is 1 over n. 1 over n times 2, 2 over n, this guy right here, and 1 over n times 1 over n, 1 over n squared. Very good. Another parenthesis here. And this is all baby middle school arithmetic. This is not even mathematics. So what do we have now? Let's do this. This summand comes out to what? 3 over n. Agreed? Now we move 1/6 through. 2 over 6 will be what? 1/3. 1 minus 1/3 is what? 2/3. So we have h times r squared times the limit of n tending to positive infinity of what? So this guy is gone. This guy becomes 2/3. Again, 2 over 6, 1/3. 1 minus 1/3 is 2/3. Now here, 3 over n and 6 in the denominator becomes what? Minus 3 over 6, 1 over 2n minus 1 over 6n squared. Now, technically, yes, we use another theorem from real analysis, which says that we can carry the limits through, provided that the limits exist, and they exist over here. Limit of 1 over 2n when n tends to positive infinity is big fat 0. The limit of 1 over 6n squared when n tends to positive infinity, another bigger fat 0. And what do we have left? The limit of a constant is a constant. And what do we have here? Well, now let us think about this together. So the answer is the following: 2 times h times r squared over 3. This is an absolutely amazing result. The volume of a hoof of Archimedes with the length of the radius r for its semicircular base and h for the length of its height over here is basically 2/3 of the product of the h and r squared. This formula is quite amazing for at least two reasons. First of all, it came out or unfolded from a very straightforward computation. There was at no point over here did we come across something that we could not handle or something that requires higher level of machinery or the introduction of new ideas. That's number one. Number two, think about this formula. What do you not see? This is the hint. What do you not see in this formula? What you do not see in this formula is our favorite irrational and transcendental number pi. You do not see pi in that number. This is absolutely amazing. Why? Well, the hoof of Archimedes fundamentally is a round object. It has the circle in it, and every time we come across a circle, pi, this way or that way, works its way in. The length of the the length of the circumference is 2 pi r of a given circle. The area of the circle is pi r squared. The volume of the right circular cylinder, if we take the whole thing again, what? Pi r squared times h times the height. So pi always works its way in there whenever we see a circle. Here, however, we do see a circle, but amazingly enough, there is no our favorite irrational and transcendental number pi. Write this result down. The volume of the hoof with the radius r and height h is 2/3 times h times r squared. So now we know the volume of our hoof if we partition that hole into smaller and simpler primitive parts that look like triangular prisms. Now we will, in an expedient manner, because we understand what is going on and where all this big train is rolling, we will model, or we will partition our hole into a collection of smaller and simpler primitive parts, each of which looks like a rectangular prism. Now we play pretty much the same divide and conquer game, but this time, instead of breaking up our hole, a hoof of Archimedes, into smaller and simpler primitive parts, each of which looks like a triangular prism, the prism that we worked with in the previous segments. This time we break our hole into smaller and simpler primitive parts, each of which looks like a rectangular prism, or basically a very thin brick. If you have a book at home, again, you can go ahead and make a model out of paper, but here is, for example, a book that my kids used to have, Animals of the World, used to read. So a relatively thin book, of course, can play a good enough model of a rectangular prism. So basically this way we cut our hole into a bunch of prisms that sit exactly like that. So what is the mechanics of this partition? Well, again, I renamed the points a little bit. Maybe that is helpful. Maybe some of you guys will find this is confusing, but let's do it this way. O is still the dead center of the circular base of the generating right circular triangle. That point is still the same. But this time, however, remember in the previous segment, this was point D. Now I renamed it into point C. This time in the previous segment, we partitioned this radius into a number of smaller line segments of uniform length, r over n. This time we take our radius OC, this guy, and we cut it up this way. And let me do a schematic for you guys over here. So this time we go like this. This will be our semicircular base. Remember, this is the point O. Here, in this case, this is the point C. And in the previous segment, we partitioned this line segment this way. This time, we partition this line segment this way. So we go this way. We partition this radius in n line segments of equal length, and then we construct straight lines that are perpendicular to the straight line OC. These lines will go this way. You see, this will go this way. These points where these straight lines intersect with the periphery of the circular base of the hoof will be on the periphery of that circle. These points will be here, and let's say the kth point will be here. It will be the point D, somewhere right here. Again, we form our smaller and simpler primitive part that is a rectangle by constructing another set of straight lines, and then we form this little strip over here. This will be our base of our rectangular prism. This prism goes up all the way until it intersects at these points the parabolic arc that is the plane of the hoof of Archimedes. This is the situation. So this point over here, I call this point is E. This guy right here. This point I called F. So this is how this prism is formed. And this point over here I call D. If you can see that, this is the point D. This is this guy. This is basically the point where the radius OC of the semicircular base of the hoof intersects the straight line that runs perpendicular to that radius, and these straight lines are of the same equal distance spaced from each other by the same distance. So in other words, if I use the red chalk, this thickness of this, see this guy, this thickness of this prism is what? Precisely the thickness of this prism is R over N, where N is a whole positive number. We play games with it. It runs 1, 2, 3, 4, 5, and so on. And we already understand the technology. Eventually, we'll make N grow without bound. The thickness of each rectangular prism will get thinner, thinner, and thinner. It will fit our volume or our solid better and better and better. And in the limit, we will claim that the limit of the sum that we're about to construct will be precisely the volume of the same hoof. And it's important to understand what does the same hoof mean. In this case, the same hoof means that we have the same radius R and we have the same height H. I renamed the points a little bit, maybe just to make sure that it's a different scenario, different setting. But here, when we connect the point O, the center of the circular base of the generating right circular cylinder, with the point B, where the cutting plane comes into contact with the side surface. Remember, BC is now the height H. I reflected it over here. OC is still the radius. And when we obtain the points E and F, as I explained over here, E and F, through these guys, perpendicular to the board, boom, we run two line segments. These are these line segments, this and this, and they will hit the elliptic arc over here that is delineated by the plane of the hoof at this point and at this point. When we connect these points, this is precisely how we construct our rectangular prism. And now, this is our second half of the first step of the divide and conquer approach, problem solving approach. And in the next segment, we will carry out the computation for the volume, which of that kth primitive part or rectangular prism, which precisely would mean a solution of each and every primitive part. Wonderful. Now we solve each and every smaller and simpler primitive part by computing the volume of the kth primitive by the kth rectangular prism in terms of the locally available material, which is what the volume Vk of the kth rectangular prism that makes up our whole. The volume of the hoof of Archimedes will be what? It will be the area of, let's say, its base, and in this case the area of this base will be what? It's a rectangle. It will be the distance FE times the distance AD. The distance AD, I'll explain where did the point D come from in a minute, times the thickness times R over N. Now, where did the point A come from? The point A came from the following construction. When we connect the point O with the point B, we get the major semi-axis of the elliptic boundary of the plane of the hoof. And then remember, from the point E and from the point F, we erect the perpendiculars to the plane of the base. These perpendiculars will actually belong to the side of the generating right circular cylinder. They will hit our elliptic arc at these points here and here. When we connect these points with its line segment. Boom, this line segment intersects the straight line OB at the point A, and once we connect the point A to the point D, this line segment will be precisely perpendicular to FE. The way these things work out, so in a way we can take it that this is the height of our rectangle that forms the prism, and FE is the length of its base, if you will. Now, what can we say about, we'll continue the computation here. What can we say about the distance FE? Again, use this as an opportunity to proceed on your own, put this video on pause, walk away from the computer, think on your own. But the distance FE, it's actually lies on the surface, if you will. Again, let's say we connect the point O with the point E. What will happen? Well, this will be the radius, and the triangle ODE, you should really write it down. Remember, from our construction, these triangles over here will be right. The triangle ODE will be right. So the distance FE from this right triangle ODE, let's write it down over here. The distance FE will be what? It will be twice 2. It will be this distance FD plus DE. But DE from the right triangle ODE by the Pythagorean theorem is what? It's the square root of R squared minus OD squared. You see? That much should be understood. There is no mystery. Again, this is all middle school arithmetic. The triangle ODE is right by the Pythagorean theorem for the distance DE, which is 1/2 of the distance FE. We have what? Square root of OE squared, which is R squared, minus OD squared. But again, if we take this as a point of origin, and remember, this is where we cut our line segment into smaller and smaller line segments of length R over N. If we count 1, 2, 3, 4, K. So what is the distance OD? The distance OD is precisely what we need. R squared minus K squared times R squared over N squared. Again, I want to make sure we all understand where did this come from. The distance OD, let me write it down for you guys over here. The distance OD is simply K uniform distances R over N. It is that simple. There is no magic over here. It is that straightforward. The distance OD is K line segments of length Rn, because this is how we partitioned our radius OC. So now for the volume we have, for the volume of our hoof, we have 2 times, let's see, square root, let's do this, R square and R square is the same term, we can factor it out. N square we can put over here, take it from under the root. So what do we have? 2 times R over N times the square root of N squared minus K squared. And now we already recognize a little bit of what we were given in the limit to begin with. That much is understood. So times the distance AD times R over N again. So here N, we get a square, so something else will happen pretty soon. So now, once I understand where did this come from, let me erase it for the next manipulation. And now we will compute or recover the distance between the points A and D in terms of the locally available material. How do we do that? Well, we do it in exactly the same way in which we recovered the similar distance in the previous case. How many right triangles that are similar do we have over here? Exactly 2 again. The triangle ODA. See, I put this right angle sign over here. ODA is right, and the triangle OCB is right. These triangles actually this time they share this, the magnitude of this interior angle. The angle over here at D is right, at C is right. Consequently, this angle and this angle over here is exactly the same by angle, angle, angle. These two triangles are again right and similar. So again, Euclid's Elements, book 6, proposition 4. What do we write? We need to find AD. We need to find the distance AD. So we write AD relates to DO, or let's say OD, in exactly the same way in which BC relates to what? To OC, to O, distance OC. And what is this? BC is H, OC is R, and from here it follows what? For the distance AD, what do we have? We have OD, the distance OD, times H divided by R. But the distance OD, we already know what that distance is. That distance OD is what? Is K copies of what? Of R over N times H over R. Again, observe the miracle of cancellations. We have R canceled. And now what do we collect? K, H over N. Let's carefully write it down where. We don't need this. I will carry it into the next line. Make sure you take your time to copy this information to your paperwork, but essentially what we need over here is grab AD, and we put this result over here. And what do we have? Let me erase this once it's understood where did this come from. This is gone. What do we have? 2 over R, 2 times R over N. Here we have times K times H over N times square root of N squared minus K squared times R over N. Now, this is just doing a little bit of an arithmetic. This is not mathematics. Mathematics was the process of generating an idea to bring in this wonderful solid known as the hoof or the wedge of Archimedes. This is just middle school symbolic shuffling. And what do we have now? Let's see. 2, let's collect everything into one place neatly. R and R, so we have 2, we have one copy of H, 2H times R squared over 2HR squared over 1, 2, and 3 over N cubed times K times square root of N squared minus K squared. And by now you guys already see where this is going. Make sure you understand everything what's going on over here, how each transition took place. If you have questions, use the comment section. But basically we use the fact that the line segment FE can be broken down into 2 line segments of equal length, DE, and DF. And for each such line segment DE, we use the right triangle ODE or ODF, if you will, to recover the length in terms of the local available material. And for the distance AD, or for the height of our kth primitive rectangular prism, we use the fact that the right triangles ODA and OCB are similar. They are right. We constructed the Euclid's Elements book 6 proposition 4 ratio, and voila, here we have it. Now I'll take a second to erase the board and prepare it for the next and the final step. But you already see what is going on. In the next few seconds we will sum these volumes, pass to the limit, see what can be carried out, what has to stay in, and thus we will recover precisely the limit that we were asked to evaluate. Excellent, we're almost done. Now that we wrote down the formula for the volume of the kth primitive rectangular prism with which we tile our hole, the hoof of Archimedes or the wedge of Archimedes. This formula is shown over here. We understand where did this formula come from. We understand each and every transition. We understand the meaning of each symbol. And now we complete our computation as follows. For the volume of the actual hoof of Archimedes, we will put I'll use the light chalk because I'll erase it, the approximation sign as what? As the V prime, which is what? Which is the sum of these volumes where K runs from 1 to N. But this approximation sign precisely tells us that even though we know how to solve each and every primitive part, we know how to express the volume of each and every rectangular prism in terms of the locally available material, as it stands right now, without the introduction of any new ideas, our composite volume V prime will not be an exact match. How do we produce the exact match? We let the number n grow without bound, which means that the width of our rectangular prisms get thinner, thinner, and thinner. They fill in the space that is trapped inside the hoof or the wedge of Archimedes better, better, and better. And when we pass to the limit, this is another wonderful mathematical object. And the ancient Greeks, apparently, they stepped on it. They were actually standing on the idea of a limit. They were standing on the what we now call integral calculus. And if we know what an integral is, we know what the derivative is, the converse operation. So they were standing on top of a lot of interesting mathematical material, touched it, but they did not realize what they were standing on and what they were touching. So here we write down the exact formula. The limit when n grows without bound, when n tends to positive infinity, of the following expression: 2 times h times r squared over n cubed. Here, the reason we factor this piece of this formula out because nothing over here depends on the summation variable k, but in the end we add this guy in. K runs from 1 to n. K times square root of n squared minus k squared. This is our result. And because what can we move through the limit sign? Through the limit sign we can move apparently 2h and r squared, because these are the constants in our case. This is what it means to have one and the same hoof of Archimedes. And now we write down the following result: 2 times h times r squared times the limit when n tends to positive infinity of 1 over n cubed times the sum over k from 1 to n, where each summand has the following structure: k n squared minus k squared, like so. And what do we see? We see that what we have here is an exact expression, or an expression for an exact volume of our hoof of Archimedes. And in the previous segments we already know that this volume is what? 2 times h times r squared over 3. How much material evaporates from here? Well, the constant 2 evaporates, the height of our hoof evaporates, the square of the radius of the hoof evaporates, and what is left? The limit. And what is the limit? What is left over here on the right hand side? 1/3. So all this work just to show that the limit in question is precisely 1/3. And on the surface, when you look at it, when you look at this limit, it is not really entirely obvious that this is a wonderful rational number to begin with. And yes, here I can totally take some amount of criticism. Some of you guys will say, look, Roman, we mastered integral calculus. We know integral calculus left and right, up and down, and we can teach you a thing or two. To which I will say, sure, by all means, I'm always willing and ready to learn. Teach me anything I do not know. But the point of this exercise is not to circumvent the wonderful, powerful, flexible, modern machinery of integral calculus, but to show how a discovery in mathematics can be made. And if you go back and watch this episode maybe a couple times, first of all, you will realize what? You will realize that all the computations that we carried out over here were not that complicated. They did not really require the knowledge above the, let's say, motivated middle school curriculum. And on the other hand, this is pretty much how many, if not all, discoveries in mathematics are made. We start with something that eventually in the historical rearview mirror becomes a baby case. Yes, this is a baby case. You guys will say, hey, Roman, we move this guy closer in or closer out, and all your computations, baby, middle school, mumbo jumbo evaporates. Granted, it does, but this is again not the point. The point is how we make a discovery. We start with something that is eventually becomes baby simple once we develop enough of new layer of mathematics. But we start with something simple because we can wrap our brain around it. We understand how to work with it. And we do not need the introduction of new ideas just to work with that baby simple whole, let's say, or baby simple situation. But then on top of that baby simple situation, we sprinkle the new idea. And this is where the tactical fight begins. This is the heart and soul of this discovery, is that we start with a whole, we shuffle around some simple ideas, but then we introduce a new idea which eventually becomes challenging and difficult to make it rigorous. Break up the whole into smaller and simpler primitive parts, solve each and every smaller and simpler primitive part, and then find a way to combine the solutions, or all the solutions of all the smaller and simpler primitive parts into a solution of the whole. In other words, the limit, the value of the limit is in question is shown over here. It is 1/3. Again, there are no pi's, no transcendental numbers. This is quite amazing in its own right, but this is it for the mathematical problem S2M44, and we will move on to a new challenge next. Our next challenge will be a problem in mathematics as well. I will keep it as slightly more difficult than our traditional problems with an asterisk. This will be the problem numbered S2M45 with a star. Because in my experience, especially in the last 7 or 8 years on Quora, is that the more people know, the less people think. And I see time and time again that the especially younger students of mathematics, judging by the answers that I read that the students generated, is that they are simply incapable of peeling themselves away from a standard cookie cutter methods or machineries and try to plow their own path through a certain mathematical material. And exactly that is what will be required of you if you want to earn your PhD in mathematics. So in the problem S2M45, using the divide and conquer problem solving approach again, we are asked to evaluate the so-called Poisson integral I designated with the uppercase p lowercase r, or p sub r. And this integral has the following structure. This is a definite Riemann integral from 0 to pi of the logarithm to the base e of the following argument to the natural logarithm. 1 minus 2 times r times the trigonometric function of cosine evaluated at the argument x plus r squared, and the integration is carried out over the dummy variable x. It is important, do not get confused or do not do the wrong thing. The integration is carried out over the x variable, and here the cosine is exactly has the argument with respect to which the integration is carried out, not r, x, dx, x. Again, in mathematics, this is frequently designated as the natural logarithm. In physics, we use the ln, but again, the logarithmic function, somehow this way or that way, is basically a wonderful and a delicious pool of international confusion, because all sorts of designations for this function existed in different countries in different times. For example, in my time, there was this guy called LG that used for something else, but for now, we will take it that log is the logarithm to the base e. We suggest that you try your hand at evaluating this integral as stated in the problem statement. If you think about it and you realize that you cannot solve this problem, then here is a hint. I will title the next episode in which I will share my solution of this problem as follows: Poisson integral by the book. That means already this title should give you a hint that in order to evaluate this integral in the intended way, in the way it is intended according to the problem statement given, you should really try to take something as a whole, break it up into a number of smaller and simpler primitive parts, solve each smaller and simpler primitive part, find a way to combine the solutions of the primitive parts into a solution of a whole, construct a certain sum, multiply something by something, pass to the limit, and obtain the limit. And again, here the reason the designation for the Poisson integral is P sub r is because r is a parameter. It is apparently a real number, and I will not say anything about the quality of that number. You guys will have to analyze that on your own. As a process, during the process of the solution of this problem, you will have to come up with a certain analysis. If r is this, then the value of the Poisson integral is one thing. If r is that, then the value of the Poisson integral is another thing. This is left for you to discover. And this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share my solution of the mathematical problem S2E42.